So to start with unit number 4, the introduction is the first type. So which is a geographic information system. So this system is a computer-based system that consists of an hardware, software, data, and application. So which provides a scientific information which has a spatial relation. So this GIS, Geographic Information System, offers the following functions: the input function, storage, checking up, manipulation or processing, integration, analyzing. It also has alphanumeric as well as a graphic representation of spatial data. So these are the main features or main functions of your geographic information system, which is being acquired by the remote sensing and being transmitted to a hardware structure. So the integration of the thematic data and information about the spatial situation distinguishes a GIS, Geographic Information System, from a CAD systems, computer aided design. This GIS is not only a tool for making maps, it is also a system for data analysis. So let us see that. So the common definition of GIS is that it is a powerful set of tools for collecting, storing, retrieving, transforming, and displaying spatial data from the real world, as suggested by Burroughs in 1986. Another definition given by Tomlinson in the year 1972 is that the common ground between information processing and many fields using spatial analysis technique is called as GIS. In 1987, NCGIA defined the GIS as a computerized database management system for the capturing, storing, retrieval, analysis, and displaying of spatial data. So another definition is that information system which is designed to work with data referenced by spatial or geographical coordinates. Was defined as GIS. So in short, or in other words, we can call this geographic information system as both a database system with specific capabilities for spatially referenced data, as well as a set of operations or working with the data, so which is analysis, which was given by Starr and Etz in 1990. So these are the different forms of definitions for GIS, Geography Information System. So the Geographic Information System has different meanings depending upon the focal point. It is a collection of spatial data, collection of tools, a package of hardware and software components, and a technology for geographic information collection. So the contributions to the GIS development was from these three. One is the informatics, which is the graphic visualization, database security, and system administration. Second one, the geography and related fields. For example, the cartography, geodesy, geomorphology, spatial statistics, all contributed to GIS. Third one is the users. So the users, for example, the public administration department, the engineering department, local searchings, planning department, geology, mining, forestry, marketing, criminology, etc. all are users. So all these three different structures or three different blocks came together as a contribution to development of geographic information system. So this is just an example of a visualization of data. The population density in the lower during 1996. You can see data is being classified according to that. If you see that if there are persons, you can see this diagram. See this diagram. So see this, for every square mile, if this color is there, this is the index. This shows that the number of persons living in this range will be 1 to 96 per square mile. So darker places you can see like this. So here for every square mile, 1060 to 8327 people are living. So depending upon this, we can find a data in a particular location. This is your United States data. So you can see the state name. State name Washington. It comes under the sub-region Pacific. State abbreviation WA. And the population in 1990 and 1996. You can easily monitor how much growth it has been done. Then in Montana, which is an area of this much, you can see that 147236028 with the sub-region MTN, state abbreviation MT, population during 1990 and population during 1996. Like this, you can see the population for all these places like District of Columbia, Illinois, Geo, California, Ottawa, Nevada, Indiana, New Jersey, Rhode Island, Connecticut, Pennsylvania, New York, Nebraska, Massachusetts, Iowa, New Hampshire, Oregon, Minnesota, Vermont, Idaho, Wyoming, South Dakota, North Dakota, Maine, Montana, and Washington. You can see. So this is a data collection and it is a storage. So with the help of this mapping, we can understand that. So during the year 1990, this was the population in these regions, and during 1996, these are the population. So the data classified are spatial trends are clearly shown. So whereas in this table, precise data, no spatial relation at all. Okay, we cannot cover the region. We don't know the region. What is this Washington? Where it is? Here Washington, where it is in this map? We don't know. We don't know where Vermont is there. We don't know where Vermont is there. Okay. So the elements of a GIS is that it has an input, it has a input and output. In between that, we have an data management. Data management, which consists of geographic data and the techniques or methods. Okay. So the inputs are your keypads, keyboards, scanners, digitizer tables. The data management system is compression of your hardware and software. Hardware is to get the data and give the outputs. The software is for manipulating, processing. Then the outputs could be your monitor, plotter, or a network or a printer. So there are 4 component models of a GIS. You can see 4 columns of a GIS and 4 tasks of a GIS. Hardware, software, data, user is your 4 columns, 4 tasks, input, managing, analysis, and presentation. And we should be familiar with which operations can be done with a GIS. The operations are what is where is what has changed since, how is the spatial spread, what happens if. So the GIS uses the spatial allocation as a common key for different data records. Different issues are connected by the geographic position. So if you see in this diagram, depending upon the geographic location, We can identify where there is a heavy people, where there are more number of people being present in this area. According to that, we can supply the raw material for their needs. If there are very lessly populated area, for example, you can see here it is. In these places, there are lessly populated. In this less population of area, we not send any that much amount of resources for food until and unless it is being required. But whereas in this darker region here and all, we need to supply regularly the food or the food resource materials, whatever is being required according to the population index. So this type of mapping is necessary depending on the geographical area. So that is what is given here. The GIS uses the spatial allocation as a common key for different data records. Different issues are connected by the geographic position. So the steps in a GIS project is that data acquisition. Second one, data pre-processing. Third one, data management. Fourth one, manipulation and analysis. Fifth one, product generation. So this data acquisition can be done by paper mapping, digital files, satellite data, field work, and obviously your remote sensed data. In data pre-processing, the preparation, integration, data conversion, digitization, scanning, edge matching, rectification, all are done in data pre-processing, where all the data which is being obtained by the paper maps, digital files, is to be pre-processed. If there are any redundant, it should be removed. Next comes your data management. So here this decides the variable selection. It defines the type of data. It tables the design based upon the performance, usability, the policies, and procedures like creating, retrieving, updating, changing, deleting, removing can be done. For create, we need to type data entry. For retrieve, we need to give view. For update, we need to give change. For delete, we should give remove. So these are some of the principles or procedures as used by CRUD in data management. Then manipulation and analysis is the step where it does address matching, mapping the address correctly, network analysis, then terrain modeling, slope, and different aspects. Then fifth one, the product generation, which consists of the reports, either in the form of tables or in the form of maps. You can give tabular reports or graphical reports in the form of maps or charts. So these are involved in a single GIS, Geographic Information System. So any queries till this? You can type in chat box. Any queries? Type in chat box, then I'll proceed for the next slide. Yeah, okay. Thank you, Sai Ganesh. We'll proceed on to the next slide. So, which is what should be possible with a GIS, or what are the things that we can do with a geographic information system? We can do automatic processing of geographical data. Automatic processing of geographical data. For example, making maps, calculation of areas or distances, calculation of slopes, route planning, traffic management, logistics, integration of data of different origins and types, linkage of data maps, solving the complex spatial relations, then the spatial modeling of complex scenarios like risk analysis, route planning, resource management. All can be done with a GIS. So for this, I'll show you a video such that you can understand in a better way. After this, two slides I'll show you. So this shows your system architecture and components of a GIS, where data is obtained. Data is obtained from your remote sensing devices or from your satellites or from your mappers or physically, whatever might be. All the data is being given to a geographical database. So that geographical database is given to a presentation and report. If there are any analysis to be done, it is given to transformation and analysis. Any corrections, then it is done. Then it is given to presentation and report. Okay. Then it is given to your geographical database and goes on. If there is any queries, it is being addressed by this geographical database. So you can see a data model for this. The discrete elements, that is near single peaks, you can see. So these are single peaks, discrete elements. You can see number one. Number two is your continuous information, that is groundwater in an area. Okay. You can see that the data models that a GIS represents is that peaks are separated apart, so which are considered as an example of a discrete element. You can see that single peaks. So whereas groundwater, which is being present, which connects all these three peaks, which is underneath, underground water. So that information is a continuous information. So keep in remembrance. So that's what I'm showing you this picture. So the discrete, as I had shown, discrete elements will have attributes like length, volume, land type, and land usage. The continuous information, you can see that continuous, groundwater is continuous. So this will have an area for an area. For example, for 1 square meter, 2 square meter, 1 cubic meter, and all, it will have only these attributes, which is temperature, content of water, distribution of precipitation, content of containments, which is your pollutants. So depending upon the data concept, there are raster, grid, GIS, or vector grid GIS. So systems working with both types are named hybrid systems. So depending upon the discrete and continuous information, the GIS can be classified into raster grid or vector grid. And some systems will employ both raster and vector, which we call as hybrid. So this is an example. This is your real world, the bottom. See at the bottom, this is your real world, which is differentiated into small pixels, latitude and longitude. So here is a water, here is a water connectivity, here is the forest, here is the grassland, here is the marshland. Okay. So in vector model, you can easily classify that like this. It will be showing. So this area will be showing it as forest, and this region will be shown as a lake, a water body. This will be shown as a marsh. So the remaining, which is present, is shown as your grasslands. So this in grid model, you can see it like this. So these are the different representations of the real world: vector model and grid model.
Geographic Information Systems Technology, or GIS, is a powerful tool for helping planners make smarter decisions about our urban environments. Hi there, I'm Mike Ernst, and I'll be your instructor for this series of GIS courses. The easiest way to think of GIS is to view it as an integrated system of components. GIS includes information about the real world that has been simplified and abstracted into a digital database, including spatial and non-spatial features. GIS is also the hardware and the software that allows for the analysis of the data. Finally, GIS also includes the user, who uses their expert judgment to produce solutions to spatial problems. That last piece, the user, sometimes that's left out of definitions, but really it's the most important part. The software is who can produce the answers without the expertise of you, the user. At the heart of GIS are maps. Maps are abstractions or simplifications of the real world that are indispensable in the field of planning. Maps are critical in helping planners understand, analyze the existing urban environment, and plan for the future. Planners need to understand a wide variety of spatial features, like road networks, land uses, where schools are located, and things like zoning districts. You also need to be familiar with conditions or events like crime patterns, traffic circulation, and environmental factors. GIS can be used to increase the efficiency and flexibility of a number of planning functions, such as open space and parks planning, land use planning and zoning, economic development, infrastructure maintenance, historic preservation, traffic analysis, tax assessment and collection, and demographic analysis, among many other factors that municipal leaders need to understand in order to effectively run a city. By better representing these elements, GIS allows planners and people planners work with to make better decisions. In the following courses, we'll be covering ArcGIS, a software package produced by a company called Esri. Because Esri software still is the industry standard, and because it has a fairly accessible interface, ArcGIS is a great tool for planners to learn. In these courses, I'll be covering some of the important concepts and theories that are critical in understanding how GIS works. Mostly, these courses are hands-on, working with software, make maps, and perform spatial analysis. You're also going to need to do some outside reading on your own of materials I'll recommend throughout the series. To complete these courses, you'll need a computer running Windows, a license of ArcGIS. If you're a student or work for a nonprofit, you may be eligible for a discount. Check Esri's website for more information. Finally, this course is aimed at beginners. If you're already familiar with ArcGIS, you might try one of the more advanced series offered by Planet courses. If you're just starting out and learning more about Esri's ArcGIS, this is the course for you.
I hope you would have seen a video on GIS, how it is being present, how it is being visualized, what are the things can be done in a GIS. I'll replay it again. You can have a view on the GIS.
Geographic Information Systems Technology, or GIS, is a powerful tool for helping planners make smarter decisions about our urban environments. Hi there, I'm Mike Ernst, and I'll be your instructor for these series of GIS courses. The easiest way to think of GIS is to view it as an integrated system of components. GIS includes information about the real world that has been simplified and abstracted into a digital database, including spatial and non-spatial features. GIS is also the hardware and the software that allows for the analysis of the data. Finally, GIS also includes the user, who uses their expert judgment to produce solutions to spatial problems. That last piece, the user, sometimes it's left out of definitions, but really it's the most important part. The software is who can produce the answers without the expertise of you, the user. At the heart of GIS are maps. Maps are abstractions or simplifications of the real world that are indispensable in the field of planning. Maps are critical in helping planners understand and analyze the existing urban environment and plan for the future. Planners need to understand a wide variety of spatial features, like road networks, land uses, where schools are located, and things like zoning districts. You also need to be familiar with conditions or events like crime patterns, traffic circulation, and environmental factors. GIS can be used to increase the efficiency and flexibility of a number of planning functions, such as open space and parks planning, land use planning and zoning, economic development, infrastructure maintenance, historic preservation, traffic analysis, tax assessment and collection, and demographic analysis, among many other factors that municipal leaders need to understand in order to effectively run a city. By better representing these elements, GIS allows planners and people planners work with to make better decisions. In the following courses, we'll be covering ArcGIS, a software package produced by a company called Esri. Because Esri software still is the industry standard, and because it has a fairly accessible interface, ArcGIS is a great tool for planners to learn. In these courses, I'll be covering some of the important concepts and theories that are critical to understanding how GIS works. Mostly, these courses are hands-on, working with software, make maps, and perform spatial analysis. You're also going to need to do some outside reading on your own of materials I'll recommend throughout the series. To complete these courses, you'll need a computer running Windows and a license of ArcGIS. If you're a student or work for a nonprofit, you may be eligible for a discount. Check Esri's website for more information. Finally, this course is aimed at beginners. If you're
I hope you would have enjoyed the video with some of the basic information about the GIS. So this was shown in your video, the real world, the vector model and the grid model. So let us see what is present in the grid model. So the grid model consists of rows and columns, each having a resolution of its own, and each cell is called as a grid cell. Each box is called as a grid cell. So vector data. So vector structure is necessary for an object-related data management in GIS, which is used for the realization of topologic structures and complex data models. The objects in the vector GIS are always points, lines, polygons. Every GIS object in a view has a representation in the database, where these attributes describe the objects and allow selections and classifications. The classifications by attributes The selections by the attributes are the two typical DBMS methods, database management system methods, that have been chosen by the special futures or GIS methods. So this is an vector GIS objects. You have geometry. You can see the geometry attributes. At this place, you can see that attributes are present: the polygon shaped, line shaped, point shaped. You can see these points, lines, and polygons in this index. Vector GIS based system. You can see the further expansion of the attributes, classification by attribute. An example of the British Columbia, the Northwestern Territory, Saskatchewan, Ontario, Nebraska of US is being zoomed up with respect to the province. This is how. This is a tool. So the tool name is ArcGIS. It is being used for this. So these are how to select the objects. Selecting objects by an attribute by geometry. So I want to select only Texas in United States. So that can be selected by using your points. So all yellow dots represents your Texas. Selecting objects by attribute and by geometry. You need to select like this. Then selecting by theme. You can see. Selecting the features of active themes with or within a those are present within a distance of 25 miles can be selected. So that is being zoomed by using this ArcView JS software. So next is representation of vector versus raster. You can see from this, making the vector versus raster. The first one is the real field. This is the real world. Forest, a river, a forest, a house, a hayfield, and a soya beans field. So in raster data, so those are being classified into grid cells. So each part is being divided into grid cells. So for that, indexing is being given. Let's see the indexing values. You can see that 1, 2, 3, 4, 5, 6 is being given for house. The maximum, which is 6, is given. For hayfields, it is 5. For the forest, it is 1. For the flow of river, it is 3. And for soybeans, it is given as 4. And for cornfield, it is given as 2. So this is how do we do griddings in raster data. So while making as a vector data for GIS, just the borders of that. So forest border is this. So then that we create a border for that. River is there, for that we create a border. So this house and hayfield is there. It is distinguished by the forest. So that is given as a border. So then this has a border. So all this makes a polygon structure. So polygon 1 here, polygon 2 here, there is a meeting. So we keep it as node. Okay. Then polygon 2, polygon 3, polygon 4, polygon 5. So wherever this distinguished parts meet the axis and meets anywhere is given as nodes. So this is how to draw a vector data, which is obtained from the data acquisition model. So always raster is a point or a cell. The line is a network. The area is a cluster. Surface is a grid. So you can see that cell will be like this. Raster will be cells. It is two or more cells connected, we call it as a network, and that forms a cluster, and that is your grid. So raster is this. Vector is that a point, then we draw a line using connections, then we connect all those connected points to create a polygon, and the surface becomes a TINS, topographic networks. This is what raster and vector is. Next is representation of vector data and raster data. You can see that same location can be done in point futures. So these are point futures represented in the grid. Okay, grid. You can see that this in the grid. Light futures represented in a grid. So this is your vec- vector data. This is your raster data. So linear futures represented in a grid will be like this for this, and for area futures represented in a grid it will be like this. So any doubts in this raster data and vector data? You can type in chat box. Then I'll proceed on further. Raster data and vector data. Any queries? Type in chat box. Since there are no queries, I proceed on to the next topic. Modeling the topographic special features. We have the 3D visualization, the color coded DTM, digital terrain model. We have the triangulated irregular networks, TIN. We have the 2D, 5D visualization of hill shadings, the mass point and break lines from surveying. All these are the special features of modeling topography. Next is the grid data model. You can see the digitalized grid data model. It uses your digital elevation model, the background showing the elevation using graduated colors and shades and shadows for visualizing 3 dimensions. So in the foreground, houses and water body are shown using the vector data model. You can see that houses are there in red. Okay, the red are your buildings and houses. The blue is your sky blue, which is going is your water body, which is goes off. These reds are your houses or buildings. These reds. This is a hybrid model. So triangulated irregular network. This is a base for developing the DEM, digital elevation model. It is a triangulated irregular network based on the measured points. You can see the same structure, the same model is this. You have peaks in these points. In this northern direction, you have peaks. That here also peaks. So this TAN was a base for the development of DEM. So that picture. So this is a 3D representation of the same tin triangulated irregular network, which are of irregular size of triangles, areas with higher and lower density of knobs. 3D presentation of a grid showing the same area but different point of view. Combination of a grid model and a vector model. The reds are your houses, the grid model is your water. Example of a high resolution grid. Visualization of a water quality data using polygons. You can see colors are based on the attributes from the database. So the colors represent water quality in the case of concentration of a nutrient, which is a pollutant. So the pollutant level, if it is 0 to 0.025, dark blue, 0.025 to 0.0375. You can see this blue. Then 0.375 to 0.05 is here, and it goes on. The field of applications of a GIS are automation of activities involving geographical data like map production, calculation of areas, distances or route lengths, measurement of slopes, aspect, view shed, logistics, route planning, vehicle traffic management, land use management, environmental planning, flood control, resource management, famine control, and others. Automation of geographical data. Google Maps is also the best example. Integration of data confined to independent domains, like taking photographs from aerial, air photos, or property mapping. So creating a boundary. Tying the data to maps permits the best communication of complex spatial patterns. For example, the environmental sensitivities. Providing answers to spatial queries, performing complex spatial modeling. For example, a scenario for transportation planning, a disaster planning, utility design, risk modeling, all are the best examples of your fields of application of GIS. So the use of GIS in practical and research fields are done in transport, traffic, logistics, facility management like infrastructure, telecommunication, surveying, urban planning, management and policy such as land acquisition, environmental impact assessments. In environmental and resource management, it is used in watershed management, soil conservation, oil pollution control monitoring, agriculture monitoring, water harvesting, water supply. And in research and development, it is used in environmental modeling, simulation and optimization of energy, soil, water, climate, etc. In scientific and engineering, the geography provides techniques for conducting spatial analysis, cartography, which is used for mapping, which has maps that have been a major source of information input for GIS, from where we get the map designs. In from remote sensing, the images from the air, space are major sources of spatial data, low cost and constitute update of input data. Everyday updation can be done by using remote sensing also. Photogrammetry, the source of most of the data on topography used in GIS is by aerial photographs for making accurate spatial measurements, infrared photographies. Surveying, this provides a high quality data on positions of land boundaries, buildings, water bodies, etc. Then geodesic, which has a high accuracy position control for GIS, uses GPS technology and gives information to GIS. Statistics, the statistical techniques used in GIS analysis are the most important to understand the issues of error and uncertainty in GIS data. Operation research contributes much by using or by providing optimizing techniques that are helpful in GIS applications such as routing. Another in computer science, the GIS uses CAD, computer aided design technology, computer graphics technology, and the visualization along with database management system for computational purposes. So far, whatever we had seen are the hardware components required for your GIS. Now let us see the software components. So the software for GIS are ArcInfo, originated commercial GIS, who is the clear market leader nowadays. Intergraph, which is strong in design and facilities mapping, running hard to match ArcInfo. Its main modular GIS environment evolved from its older CAD products. The development of a new generation product of its own, named Jupyter-based NT and object technology. The next software is the Bentley Systems, originally developed the PC-based MicroStation product Geographics in cooperation with the Bentley Systems that was built in 1995, which had a very successfully and continued to develop and sell MicroStation Geographics. Next is the Autodesk's AutoCAD mapping. So this dominant CAD supplier and software company, which used fully topological AutoCAD maps since 1996, illustrating the convergence of CAD GIS with many industrial applications of AutoCAD for mapping. Then we have the Graphic Data Systems, which originated as McDonnell Douglas in-house system, industrial applications, visualization of technical products, which is now used for mapping the environment. Next is the ERDAS or Image ER Mapper PCI NV. This origins in remote sensing raster and vector data, which is obtained by the new satellite data products. ER Mapper originates in Australia, PCI originates in Canada. Then the GRASS, it is a public domain software with the raster oriented features and having some vector oriented features also. Next is the CCAD, comparable with the ArcInfo powerful GIS with a lot of functionalities for raster and vector data object was being done with object-oriented database structuring. Then IDRISI was being developed, which is comparable with the ArcInfo, but it is not that much powerful. Then we had the MapInfo, which is a small GIS used for planning purposes, easy to handle. So this is how the software process occurs in data systems. The user requires some data, it is being planned, data input is given, data is stored, data is analyzed, data is given as output depending upon the activity. It starts from here. 1, 2, 3, 4, 5, 6, 7. The data structures are being classified into two different types. One is non-spatial, another one is spatial. So spatial in the sense all the geographical features from the earth, coordinates, environmental information system, infrastructural information system, cadastral information system, socio-economical information system, all comes under spatial, which is obtained by the satellites or the remote sensing or by aircrafts or by balloons and so on. And next is this non-spatial data structure, which is obtained by the transportation, management information system, finance, library, communication, decision support systems, office automation, artificial intelligence systems. This comes under non-spatial. Next is the GIS data structures. The GIS is a graphic data structure with multiple graphic data layers and their databases being present. So the traditional computer file structures that allow for the storing, ordering and searching of pieces of data is being used at a higher level of organization in the computer, called the database structure that allows more complex methods of managing the data being obtained. So let us see the spatial data. So the points lines, areas that you had seen can be represented by their respective symbols. These are the real world phenomena of point representation, line representation, area representation, and a volume representation. Point objects are a tree. Point object in real world is this. So a point object in cartographer's conception of line representation will be given like this, a bold or plain. The real world, an animal is represented as like this. So animals, if they are present like this, the area representation will be like this, animals range. In volumetric representation, if the house density is like this, it will be represented like this in volume representation. You can see from the diagram. You can see this. Next is the airport. In cartographer's conception, it is given like this, aircraft symbol. And highway is like this. And area representation, like watershed or water streams, like this. Streams like this, watershed like this. Hedge row densities can be represented like this. Chemical spills like this. Power lines, right ways, movements can be done like this. New subdivisions like this. Polygonal structures. Areas developed and undeveloped can be classified like this. Open pits and mines like this. River valleys and rivers like this. Irrigation dams like this. Acre feet of water like this. So what all comes under point features that we had seen in this diagram? Let us see. Point features, trees, houses, roads, intersections, all comes under point features. These objects are assumed to have no spatial dimension, so each can be referenced by its location coordinates. So these are said to be discrete in nature, that it can occupy only a given point in space at any time. Point features. Line or linear features. The roads, rivers, regional boundaries, fences, hedgerows, or any kind of object that is fundamentally long and very skinny comes under the linear or line features. They are conceptualized as occupying only a single dimension in our coordinate. So line coordinate single. So other lines such as political boundaries have no width dimension to be concerned about. In fact, they are not physical entities at all, but rather a construct of political convention and agreement. So they allow us to measure the spatial existence by simply finding how long they are. That's all. So 2 points, a beginning and an end point, will be represented. The more complex the line, the more points we need to indicate. Next is areas. Objects observed closely enough to be clearly seen to occupy both length and width are called areas. Line and area. Two-dimensional objects include the area occupied by a yard, the aerial extent of a city, or an area as large as a continent, are all areas. Surfaces are continuous data like hills, valleys, ridges, cliffs, where adding the dimension of the height of our area features allows us to observe and record the existence of surfaces. Next is the spatial measurement levels. The objects themselves are called as entities or coordinates. The spatial features or entities also have additional information besides spatial information. The additional non-spatial information that helps us describe the objects we observe in space comprises the features attributes. So let us see that. The points, interval, and ratio. So each point will represent each dot. Each dot represents 200 objects. So depending upon the object or the dot size, we can identify how much range it is. For example, 0 to 5,000, 5,000 to 10,000, and 10,000 and above. Interval or ratio in points. So in line, the flow of lines will indicate contours depending upon the distance. 20, 30, 40, 50, 60, and it goes on. Population density. Density of population in this zone is this much. This zone is this much. The other zone is this much. So lighter indicates lesser. Darker represents heavier. So population per interval can be done. Then small, medium, large points can be determined in ordinal. Then in line we can have the differentiation between country road, state road, highway road, interstate highways in US. This is an example of US, so it is given as US highway. Then business districts, primary, secondary, smoke plum, etc. Then differentiation by points is town, mines, benchmark, with a line, roads, boundary, streams, water body streams, deserts, forests, swamps. In order to explain these concepts in a better way, the point, line, and surface, I'm going to show you an live experiment of the Thar Desert. Okay, you can see. I think you are able to see a map which consists of Thar Desert in my search. I'm moving the map towards the Thar Desert. Okay, so you can see that there are yellow color lines. Okay, yellow color lines flowing here and there, and here there are points. For example, here if I point, it is a Bikaner, here Nagaur, here Jodhpur, Ajmer, Bewar, Pali, Balodra, Barnamer, Jaisalmer, Pokhran. Okay, all these all are your representation of your points. Okay, these points are being interconnected. You can see. Not this. Yeah, yeah. These are examples of your points. And the Bikaner and Pokhran is connected. The Nagnur and Jodhpur is connected. The Nagaur and Ajmer, Nagaur point and Bewar point is connected. It is an example of your line. Okay. And area, you can see that If I zoom it in, it will show your area. For example, this is your polygon structure, this is your polygon structure, it is an area. And see this area, when I zoomed in, it is showing a different area here, a blue color. Here some gap and a blue, here some gap and a blue, here some gap and blue. Here, see, here is a area. Here is an area. Okay, so this is area or a surface that we are seeing here. Point, line, and area. And depending upon the application or the interval ratio, we can find what it is. Now I had shown you an normalized route map view. I'm going to change this map into an satellite view with respect to your satellite. From satellite, if your camera is there and if it is seeing how this will look like, the same place. I changed it to an from map to satellite view. So I'm going to zoom in Jaipur. Okay, my resolution is increasing. You can see that. My resolution is increasing. From 5 km, you can see here. From 5 km distance, how this will look like. Now I'm increasing. I'm zooming from 2 km. From 2 km resolution, how it is, how the Jaipur is there. And I want to zoom it again. For 2 km, this is how this Ghat Ki Guni, which is present nearby Jaipur, is looking like in Google Maps. I would like to zoom it again further, 1 km. Okay, now I am able to see lot of places. I can see a Raja Park, I can see a Central Park, I can see a Moti Dangri, I can see a Jaipur, RTO Jaipur, I can see a Baba Mandir. Okay, I would like to further move on. I am zooming it for 500 meters. You can see 500 meter. I am able to see there is another called Dev Vihar Colony, Kya Naguri hai, Paldi Meena, some places, and it is able to show me some places like H. Okay, H represents your hospitals. Okay, you can see that H, all the locations which are being present shows your hospitals. And if I see this green color, these all are marriage halls. Okay, you can see this is a gardens. And if you have Om symbol, this represents that those are worship places, temples. If I move further, you can see that here this symbol is there. This is a Jahur Kala Kendra, which shows this symbol is a museum symbol. Okay, and I further move on to some other places. I'll show you in an urban area. So this is the shape of a basket, which is a shopping mall, shopping place. Then here I'll show you different signs. Here is a place of meeting. So this symbol is a meeting. Rajasthan Vidhan Sabha. Here location of a train station. So this metro train symbol. And here a symbol of Om is there. Om symbol represents your temples. Further I cannot zoom it. So that's all. 500 meter is the maximum resolution being provided. I think so. Let me check it out. Yeah, it's moving. Yeah, it's to 100 meter, right? 100-meter resolution. So the Jaipur city will look like this. A Tilak Park is there, a public school, which gives you degree, and after the UG, after 10th. So here there is a symbol of fork and spoon, which is a hotel or eateries. You can see a ground. The symbol is for ground. Suraj Maidan, hospital, parks, parks. This is a sports club. You can see, you can zoom it and see. A symbol of cash, which is meant for banking. Then you can see here. Now, now you can see a hilly region in this Jaipur. The roads are being going. So this is asphalt visualization. You can see that this is a road, a state highway or a national highway. So this is a national highway. This is a state highway going. So these are your streets. These small whites are your streets. These green are your vegetation parts. Here this brown is your mountains. These are your trees. I'm zooming out the Jaipur. Now you can see how the satellite view of 200 kilometers from the above the surface of the earth. We see how India will look like. So the greenish structures indicates that there is a good vegetation. The whitish structures shows that they are dry places or the desert places. The brownish structures show that they are mountainous regions, and the blue you can see here, all this blue is all our water bodies. So all this data that I'm able to show you is with the help of your GIS, which is being done on your Google Maps. Okay, which uses your, see here, imaginary copyrighted 2021 terametrics map data 2021 is being used. And say the star. This is the star is my location. Now I changed from the satellite view to another view. So this shows your grids. So the district boundaries, so the state boundaries you can see here. So this dotted black are representing your state boundaries. State boundaries. This is your mapping views. Map.